také měříme na jižním pólu, hluboko pod ledem. A na začátek bych ještě rád řekl nějaké technické parametry. Vysíláme teda na YouTube, vysíláme na Twitchi, streamujeme. Můžete se tam ptát jak v angličtině, tak i v češtině a během toho přenosu vám bude odpovídat náš kolega Jan Eber, Jan Tomáštík na vaše otázky a některé z těch zajímavých otázek potom předáme i panu profesorovi. So now I can switch to English again. It is a pleasure to welcome Professor Francis Halzen here in the Czech Republic in Olomouc. Professor Halzen is a very well-known physicist. He comes from the University of Wisconsin-Madison in the United States, and he is leader of the IceCube Neutrino Observatory, principal investigator. And he will tell us about this nice experiment and nice project. We are broadcasting, streaming on YouTube and Twitch, so you can ask questions in chat also using this internet connection. So Professor Halzen, floor is yours.
Thank you very much for this kind introduction. It's a pleasure to be in this beautiful place. It's a pleasure to give this talk because in 20 years when people think of IceCube, they will think, well, you buy photomultipliers in Japan, put them in the ice and you see cosmic neutrinos. It didn't quite go like that. And so I realized one of the last times I gave this lecture was in Rio de Janeiro. And I looked at the people and I said, nobody in the audience here knows what ice fishing for neutrinos is. So I don't know if you know, but where I live, it gets very cold in winter. In fact, often colder than at the South Pole. And then you can walk on the lake and you make a hole in the lake and you catch fish through the hole. That's what we are doing at the South Pole, but we catch neutrinos. So this takes a while to explain. It's very long and painful, but I'll try to make it easy. I'm going to explain to you what a neutrino is, even if you know it already, what neutrino astronomy is. I'll then tell you what IceCube is, and then show you the first maps of the sky and the first stars in neutrinos. What's a neutrino? Well, if you remember your high school physics, you were told that when you put protons and neutrons together, you make nuclei. And when you put electrons around the nuclei, you make atoms. And that's what the whole world is made for. That's particle physics. Beautiful, simple picture. Well, it's not quite right, because here are the three particles that were known in 1930, and people started doing experiments in Cambridge, England, and they noticed actually that a neutron would transform itself into a proton and an electron. Now, even if you don't remember your high school physics, you know that if I am the neutron and the proton goes this way, the electron has to go that way. It has something to do with momentum energy conservation. And they saw situations where the proton and the electron went that way. And that violated all the known laws of physics. And there was a simple solution to that. If you see the proton and the electron go that way, then the neutrino goes that way. So they invented a particle called the neutrino that restored the laws of physics. And you see, they actually discovered the neutrino. By this method, we detect new particles at CERN and at Fermilab and all over the world. It's called a missing mass experiment. So, but at the time, only 3 particles were known, and they couldn't imagine they had discovered a new particle. So for a long time, the neutrino it wasn't clear whether this was some mathematical trick to save the theory or whether it was a real particle. And so it took quite a while. In fact, it was this man, Pauli, who dreamt this up in the end. And he said, I've done a terrible thing. I have invented a particle that cannot be detected. So the idea was that this was just a ghost in the particle, in the list of particles. And that was disproven finally when Reines in 1956 discovered the neutrino. So the world is actually made because, as it said on this slide, changing protons into neutrons is nuclear physics. And so you can think of the neutrino as an agent that makes nuclear physics possible. And without nuclear physics, we wouldn't be here. So it's not only known now to be a real particle, but it's part of this, that's what the world is really made of. And of all these particles, the neutrinos is actually the most common one. There are more of them than protons, neutrons, and electrons. So neutrinos are everywhere where nuclear physics is. So, for instance, if I start at the bottom left here, the sun is a nuclear reactor. So without neutrinos, the sun wouldn't shine. The Big Bang wouldn't have happened without neutrinos, and stars wouldn't explode without neutrinos. And if stars didn't explode, we wouldn't exist, because we are made of the stuff that is born in the explosions of stars. Now, we produce now these days neutrinos at reactors. You emit neutrinos because the salt disintegrates in your body, quite a lot actually. And this is a critical picture here. This is a nuclear reactor. And when you see these pictures of nuclear reactors, they of course cover them with water because particles come out of the nuclear reactor and they're not good for you. So the water absorbs them. And look what particles do in water. They turn the water blue. Remember that. That will come back later in the talk. Another place where neutrinos are produced is in the atmosphere. The atmosphere is bombarded by cosmic rays. I'll tell you later what that is. The details are not important. About 20 kilometers above our heads, they interact with nitrogen and oxygen, the atmosphere, and then they produce pions that decay, and you see 3 neutrinos, and also muons, which are very annoying in these experiments, as you will hear later. So in other words, the atmosphere makes neutrinos as well. You want to do astronomy, you want to look through the atmosphere, right? Well, that's a science, because there's like a cloud of neutrinos that never goes away. Now you know what a neutrino is. What's neutrino astronomy? This is astronomy. Astronomy is, this ellipse. And what you do is, when you go out at night, you look at the sky, and your eyes catch not neutrinos, but light. And in the way I will project the sky, this represents the whole universe, and it's on plotted in such a way that the main axis here of this ellipse, that's the plane of the galaxy we live in. So if you look out at the sky at night, I don't know if here you can do it, but what you see first is the plane of our own galaxy. You see the stars that are close to us first, and then when you look farther away in the background, you see light from stars that come far outside our galaxy. So that is astronomy as we know it. You can do astronomy in different ways. This is visible light, You can then decide, I'm going to change the wavelength of the light and look at the sky in a different way. So you can go to more red wavelengths. You could use red light and make a picture like that, not with your eyes, but with special apparatus. And when I go to the red light, at some point, actually, I reach a point where the universe looks like that. And you see it looks totally different. This is called the microwave background. And it's important in this talk because you realize the microwave background means that in every cubic centimeter in this room and in the whole universe, there are 411 photons per cubic centimeter. So the universe is not empty. There's all kind of stuff in it. But the densest thing in the universe is this microwave background. Then I can go to blue wavelengths, and then the sky looks like that. So each time you look at a different color of light, the sky looks different. You see new things. The things you have already seen, you see in a different way. You learn new things about it. This is a fantastic game to play. The problem is, at some point when you go to bluer and bluer light, the universe turns dark. You don't see anything anymore. And that's due to the microwave background. So if you see here this sequence of changing the wavelengths of light and seeing the universe in different ways, looks at this picture in X-rays, totally different again. But this stops. And the reason it stops is if you have light emitted very far away, somewhere deep in the universe, that photon is making its way through this 3-degree background, this cosmic background, 411 photons per cubic centimeter, and eventually it will hit one. And what then happens is that it makes an electron and a positron pair, and when these are charged particles, with charged particles you cannot do astronomy. And we know that in a painful way. In fact, the interesting thing is that when these cosmic rays I mentioned before, the universe here, there is no light. But the highest energy particles that reach us from the universe are actually particles. They are not light, they are protons, they are helium, they are nuclei. For a long time, people thought when they saw these protons coming from the universe that they were really very blue, high-energy photons. They are not. So this is the universe of cosmic rays that we cannot see in light. The problem with cosmic rays is, just like with the charged particles that you form when the photon is absorbed on a microwave photon, is that they are bent in magnetic fields. So even if in the universe the magnetic fields are relatively weak, we don't know them very well, they will be bent, but before they reach your telescope, they will be bent in the magnetic field of our own galaxy. And so you cannot do astronomy. A proton can be produced there and you detect it there. So the sky map gets scrambled. So the idea was to do astronomy with neutrinos. This is not an original idea, because the man who discovered the neutrino told me one day that as soon as people knew the neutrino was real, literally everybody had the idea that we had to do astronomy with it. Well, it took half a century, but we finally did. So the neutrino that's produced in these stars, they will come all the way to our detector. They come from the beginning of time, from the edge of the universe. Nothing can stop them, including your detector, of course, which I'll come back to next. So is this interesting? Well, you know, it's a new astronomy. And so, but the motivation of most of us to try to do this was to detect where these cosmic rays come from. And they were discovered by this man in 1911, and so we are now 110 years more, actually, later. And we know that some of them come from outside the galaxy and some from inside the galaxy. But, you know, a century later, we had all kinds of theoretical ideas where and how they were accelerated, but really we had no clue. And so we hoped that neutrinos would finally solve this problem. It's a fascinating problem, because some modest experiment in Utah in 1991 discovered this particle that has a 300 million TeV energy. So to scale this, the energy of the particles made in Geneva in the Large Hadron Collider have an energy of 14 TeV, 1/4. So you wonder, how can you not, be obsessed by finding out how nature does it? We don't even know where nature does this. And so if you use LHC magnets, actually, you would have to fill the orbit of Mercury to accelerate that particle. And that's not how it happens, we think. The other reason, deep inside of trying to do this astronomy, is that you want to join this table. This table comes out of an elementary astronomy textbook. It could be a high school textbook. In fact, some of the history in this table is terrible. But the idea of the table is that when you look at the sky in a different way, you always see something new. And it was never anticipated. You could never predict it. Of course, otherwise it would not be really new. Like the optical telescope was developed in Flanders to look at the ships that were coming from England. And if you saw first what was on the ship, you could sell it first. And they were called spy glasses. And there is no evidence that any astronomy ever happened. But Galileo was told about this, a tube with 2 lenses, and he knew optics. And he instantly built a telescope that was 30 times better. And of course, he did look at the sky, and he discovered these patterns on the moons and the moons of Jupiter. It was an incredible experience. When you go to the end of this table, gamma rays, the military actually built fantastic gamma ray detectors, this very blue light, and they were built to look, they were put in satellites, there were 2 satellites, and they were built to look for thermonuclear explosions in the Soviet Union at the time. They never saw any, but they would turn their sensors up to the sky to calibrate them, actually on the Vela pulsar. And there they discovered what's still one of the great mysteries of astronomy, which is gamma ray bursts, which we're also trying to study with neutrinos. So as I said, you want to join this table. This happened to every new way of looking at the sky. So unfortunately, during the time since the discovery in '56, and now people were trying to figure out how big a telescope you needed to detect neutrinos from our galaxy or from outside our galaxy. And so they came up with this terrible result that you probably, if you wanted to have a chance to see something, you had to have a square kilometer mirror, which meant you had to build a kilometer cube neutrino detector, because you don't detect neutrinos with a mirror, unfortunately. We know how to detect neutrinos. This is a picture of one experiment. It's the biggest one ever built in the Japanese Alps. You need water and you need light sensors. And unfortunately, the theorists told us this experiment is 10,000 times too small. So you don't give up. The idea of how to beat this 10,000 was already known in 1960. This man, Markov, I won't read what he said there, but this is a cartoon of his idea. You want to detect neutrinos, you look through the Earth. You don't look up. You look up, you see all this horrible stuff coming from the atmosphere. But if you look through the Earth, only neutrinos come through the Earth, so you know you detected a neutrino. What does this neutrino do? It does nothing. It has no charge, so it doesn't leave a path, and it will fly through your detector. 1 in a million times about for our experiment, it will actually hit a nucleus, not an atom. It doesn't see atoms. It will hit the nucleus head on, make this small nuclear reaction, and make the splash of particles. But you know what, from looking at the picture of the reactor, if you make a splash of particles, that makes blue light. And among these particles, there are particles like the muon that will carry this blue light over kilometers. And if it reaches your detector, you can map this blue light and not only detect a neutrino, but figure out where it comes from. So I told you this already, so these particles are called muons. And they go at the speed of light. All this is happening at high energy. But the light they make when they tickle the atoms only goes at the speed of light in the water, which is 3/4 of the speed of light. So it makes a shock wave. It's like a speedboat that goes faster than the waves on the water. And so you just map this and you know the direction of the muon, and it's aligned with the neutrino. So here is actually a picture. These are light sensors. Each of these little dots on these strings, the ones that are lit up detect light. If you see a big, they detect a lot of light, and you follow the rainbow red to blue, and so you see how the light recognizes the direction of this muon. So the neutrino interacted somewhere here, made charged particles, and the muon carried for more than a kilometer the information that the neutrino was created through the detector. If this is not clear yet, here is the movie with the speed of light slowed down. This was tried with a collaboration of US and Russian and Soviet physicists who put optical sensors in the ocean off the coast of the main island of Hawaii. And unfortunately, that experiment should have succeeded, but at some point, their funding was cut off, and it was never built. I think it could really have succeeded. So in the late 80s, we had the idea at Wisconsin to do exactly what they were doing, but to put the photomultipliers, the detectors, melt them in ice instead of putting them in the water. Now you said, that's crazy. Must be easier to put them in water. Well, no, it isn't. And so that, we had thought this through, and maybe we were naive, but we thought this was going to be easier. So where do you find ice? Well, the obvious place is the South Pole, right? So this detector, everything is built at the university in Madison, and then it goes by plane or boat to Christchurch, New Zealand, and then all the equipment goes from Christchurch, New Zealand to McMurdo, which is a base on the coast. It can also go by ship. But from McMurdo, everything has to go in transport planes to the South Pole. So when you get to the South Pole, the critical thing is you have ice. You stand on 3 kilometers of ice. And when you look at the ice, that's what it looks like. It's a desert. There's absolutely nothing. But if you look in the other direction, you see there is a station. And that's critical because there's not only a station, there's like a small village with all the equipment that you need to build this experiment. It already existed. In fact, this was a news station. That's what it looked like in the winter. And that's an important picture because it means it's a base, actually, that you can access the whole year. You don't have to turn your experiment off every 6 months because it's 6 months winter. And there are no planes going in or out during winter. So I cannot show you a picture, but imagine this is 3 kilometers of ice. This is what the ice sheet looks at when you reach the Indian Ocean. And we had a long campaign of studying the optics of the ice. And so we made this incredible discovery that the blue light made by charged particles in the ice can travel 100 meters. In some layers of the ice, it can travel like 200-300 meters. And so this is the clearest solid that nature ever produced. And we understand why. So the ice in the South Pole, in the detector is at about 2,000 meters. And that's snow that fell on Antarctica 65,000 years ago. And it's infinitely pure. So this ice is made out of condensed snow, about 2 inches every year that accumulate. But because of its purity, it's ultra transparent. And so, of course, the light travels far. You don't need as many light sensors to detect it. So here is a picture. That's the South Pole Station. This is the runway where the planes land, and this was the IceCube construction. So how did this project start? Well, we had this idea, we had to do something. And I was a theorist, so I didn't have a lab. I had 3 students who were all theorists. And so I removed the ping pong table from the theory group, threw it out, and changed the room in a lab. And we built these optical sensors. They are, in this case, 8-inch light sensors, photomultipliers you buy in Japan. And you put them in a pressure vessel and try to put them in South Pole ice. There were 2 respectable physicists here. This is Seraptilov, some of you may know, who is still with the project, thank God, because we couldn't do it without her. And this is Bob Morse, who is now retired, living in Hawaii. So the easiest part is the light sensor. It's like the size of a basketball, and it looks like a big light bulb, but instead of emitting light, it detects light. So the whole idea is now you melt the ice, turn it into water, sink your detectors in the ice, and then let it refreeze and take data. So in the year 2000, we had built a small detector. And it consisted of 500 of these modules that you saw on the picture of the lab in Madison. And so this is actually a picture from the year 2000. This was the South Pole. It moves 10 meters every year. It was there in 2000. And this is the Amanda building. And so if you went 1.5 kilometers deep, there were some 500 photomultipliers. And this was the most exciting moment of the project. Nothing ever before or after compared to it. I remember the day I walked in to my student's office and saw this picture. This is, each of these dots is one of these basketballs. And you see here a muon coming through the detector, lighting up the photomultipliers. And this is exciting because once I saw that picture, I knew this would work. You know, it was kind of scary because by that time we had spent a lot of money and we had no idea whether it could work. Now, you see, these are, of course, these neutrinos made in the sky. It doesn't matter. They're totally uninteresting, but the technique worked. And so then we were unstoppable, of course. We published this in Nature with the claim that we now knew how to build a kilometer cube detector, which was outrageous, but it worked. And we were helped by The Economist, who wrote a whole article on this experiment. And you see, we peddled that to the National Science Foundation. And I must point out that it's not always as easy, but this is not me. So then it became an industrial organized project. It became very boring. And you see here all the photomultipliers. Instead of 500, it's 5,000. And it's the same story. You go 1.5 kilometers deep, and you have a cube of ice. It's hexagonal, which is a detail, filled with 5,000 light sensors. They are a bit bigger and a bit better than the ones in the R&D project I mentioned before. So if you could go in the ice, which is impossible, you would see a string 1 kilometer long with every 17 meters a sensor. So there are 60 sensors on a string. If you go, oops, no, I don't want this yet. If you go 125 meters further, there's another string. You go 125 meters further, it's another. And here you see the key, the fact that this light travels hundreds of meters. You know, imagine the light. In fact, the glaciologists thought that this light had an average absorption length of 8 meters. This would never have worked. So it was this serendipitous discovery that made this experiment possible. And so 86 of these strings fill 1 kilometer cube of ice, and that's IceCube. And so now the question, how do you put this stuff in the ice? Well, the first 100 meters is simple. It's just snow. You melt it. Then it becomes harder, and then there is this hot water drill, which is just a nozzle that puts out water under pressure. And it falls by gravity, and after 2 days it has melted ice and turned it into water over a volume that's good enough to deploy your equipment. So what this nozzle delivers 200 gallons per minute, and it corresponds to, you have to produce power, and the power, 4.8 megawatt, is produced by 40 car wash heaters. That's all. So it's kept very simple. You see the whole system is on sleds. You saw the drill tower. This is a 2.5 kilometer hose that goes in one shot to 2.5 kilometers, melting the ice. These are the housing with the car wash heaters that are just driven by generators consuming regular fuel that cost $11 a gallon at the South Pole at that time. So after 2 days, the drill comes out, the hot water drill comes out of the hole, but ice is an insulator, so that water stays liquid for many hours, typically a day. And so now you move to the next side, and so now you have this water hole. And so here are the 60 light sensors that are ready. And so now, in the next frame, you are going this cable. We attach every 17 meters one of these sensors, and then let the whole thing sink to the bottom. And you wait until the water refreezes and take data. You realize that's the last time you see them because they never come out of that ice again. But it doesn't matter. They're totally stable once deployed. It's all good. So I think I said all that. So here a picture. So you can only work at the South Pole in November, well, mostly December and January, 2 months a year. And so this season, this fantastic crew that drilled 86 holes without failing once had deployed 20 of these holes. And so here you see the cables. They go into this building, and these cables take down the voltage to power the sensors, but they also bring up the light signals. The light signals are digitized and in digital form brought back over the same cable to this place, which is a 2-story building filled with computers. And so that's IceCube. So here you see IceCube in action. You see all these tracks. So the computers collect these signals from these 5,000 plus photomultipliers and build them into tracks. And you see, for the experts, you see a muon bundle coming from above, a cosmic ray muon bundle going through the detector. What is this? Well, unfortunately, these are neutrinos produced in the atmosphere, and even worse, they're cosmic ray muons that hit us from the southern hemisphere at incredibly high rates. And so the movie you looked at, you noticed it repeated, it's 10 milliseconds long. And so what this means is that what this detector sees is 100 billion atmospheric muons every year, 3,000 every second. Atmospheric neutrinos, 100,000 per year. That's interesting, because that you can do very interesting neutrino physics with, but not astronomy. And then we were looking for cosmic neutrinos, praying that the theorists were right, that we needed a kilometer cube detector. And this was very nerve-wracking, actually. During this period that we were collecting our first data, I want to show this. New Scientist published this website, and you could actually bet, literally, I'm not making this up, you could bet on big science projects whether they would succeed or not. And so you can see here, let me point out, the Large Hadron Collider there, the probability of detecting the Higgs, you could bet 6 to 1. LIGO, in the interferometer, you could, the probability they would detect gravitational waves, 500 to 1. And you cannot see it because it's written at the South Pole that Amanda, which was by then IceCube, would detect cosmic neutrinos, was also 6 to 1. And I can tell you, this devastated me. You know, and I realized that this was a big gamble. You spend a large fraction of your life on. It was not funny. And so we actually, I was inspired by my friend Alan Watson. We started betting on LIGO. And a lot of other people must have done that, and they took the website down, and that made me happy. So we completed the detector and started taking data, and we were looking for something I won't explain to you, but which is really easy to detect if it existed. As far as we know up to date, it didn't exist, but it doesn't matter. While we were looking to the data, we suddenly found this event. And this event, you know by now what you're looking at. It's like a bomb of light explodes in your detector, and you don't see a muon track, it doesn't matter. You know, when we see this picture, this is actually the online display of the experiment, we can just look at the size and we can tell what the energy of this neutrino is. This is an electron neutrino instead of a muon neutrino that makes these muon tracks. And so this neutrino had an energy of 1,000 TeV. And it's unlikely, but not totally impossible, that neutrinos of such energy are made in the atmosphere. And in the 2 years of data we were analyzing, we actually found 2 of these events. And now you have to realize what these events look like. They fill half a kilometer cube detector. So I've superimposed this event on the data center in Madison, Wisconsin. And you see they have the size of about 5 city blocks. And so there, with all the light we detect from these events, we detect, in technical terms, more than 300,000 photons in this picture. And from this information, we can reconstruct the energy very well. So never mind that you can tell by eye, you cannot publish that. So we actually have an energy resolution. We can tell the energy by about 10% of its value, which it makes very likely that this was, these two events were not atmospheric neutrinos, that they came from the cosmos. In fact, one of them came from right off the center of the galaxy, which led us on a wrong path for a few weeks. So what do you do? Well, you found these two events, that's great. Let's do this, let's go back now. We found them by accident. Let's go and look for them, which was easy. You look for big balls of light in your detector with no light coming in from the sides. And so we designed an analysis like that and looked again through the 2 years of data, and we found 26 more events. And that, of course, gave us enough courage to claim. You see, they were all named after Muppets. And so I told everybody, our goal is to run out of names of Muppets, and we did. So we published these 28 events. Here I cannot help showing you all of them. And claimed that we had discovered cosmic neutrinos. This was not an easy paper to write, but after a lot of discussion, we got the courage. This was November 2013. In the beginning of December 2013, we were declared the breakthrough of the year by Physics World, and that made us very nervous, I can tell you. So by now, we have discovered neutrinos 4 times over again with different methods. There's no doubt about it anymore. So what does the sky look like in neutrinos? This is one neutrino sky map. What you are looking at is, in this huge background, you are looking at a map where we think that these neutrinos have a chance more than 50-50 of being coming from the cosmos. And of course, some of them, a few of them we are sure, they're 5 sigma with one event. Some we are not so sure, but that they are all more than 50%. You see, this should give you a picture of the sky. And the first thing you notice, there is no concentration in our galaxy. So we are not seeing our own galaxy. And so we are seeing the whole sky, the whole universe. But our galaxy doesn't stick out. This is not true in any other wavelength of light. And this is very interesting fact. So we are seeing extragalactic sources only, at this point at least. So, as I said, this is what it's supposed to look like, and that's what you see, the pictures I showed you of the galaxy in different wavelengths of light, they all look different, but they had this big band in the center. We don't have that. The other surprise is when we started counting our neutrinos, we realized actually that there are more of them. This conservatively says it's an older slide, that the number is similar to the number of photons in the universe. So, you know, neutrinos were supposed to be something exotic. They are not. They have the energy in the universe is neutrinos is actually higher than the energy in gamma rays. And of course, this was not only a great opportunity to do astronomy, but also to do the astrophysics and figure out what's going on in what I call the dark universe. So where do they come from? And so for 3 years, You've seen this map. For 3 years, we spent our time trying to correlate this map with anything astronomers knew about, and that's a lot. You know, we could have done this for 30 years. But after, and without any results, nothing. You know, not even 3 sigma by accident, nothing. And we kind of begin to understand why this game didn't work now. But so we invented a new game. And the new game was when you see an event going through your detector, the computers, as I explained, at the top of the ice, do a first reconstruction. That's further improved, that's then sent over satellite to Madison, and then further improved. We decided to send this first reconstruction as an astronomical telegram to the whole community. You know, that takes some courage. It's like throwing your data overboard without looking at them. That's literally what we did. And so the reconstruction in the 2-story building goes over Iridium, actually, directly to a website that all astronomers look at, and then they can, you know, follow up or not. We actually had no idea whether anyone paid attention to these telegrams until in 2017 we sent this alert. There's nothing special. That's all you send. It has the coordinates, and this one actually doesn't even have the energy. We get these on our cell phone when they happen, and we have some more information. I noticed this doesn't have, but it was this event, the 17th of September 22, and it had an energy of 290 TeV. That's a cosmic neutrino, unless you're extremely unlucky. And so it comes from just below the horizon. In fact, it comes from the shoulder of Orion, and it points right at an active galaxy, which is actually a blazar. Within 0.06 degrees, actually, it pointed at this blazar, which was known from gamma ray observations. And that, it also was in a high state, which makes it even more special. So it was really accelerating at a high luminosity and producing photons. And so the probability that this happen, you can calculate in several ways, but it's 1 in 1,000. Now, given everything we have done, 1 in 1,000, you know, at some point this happens by accident. You will run at something that happened 1 in 1,000. But what made this event interesting, what happened afterwards, it was discovered that it emits 100 GeV gamma rays, so it's what we call a TeV source, and that makes it even more special. That, you know, now the plot thickens. And this is a long story, and eventually every wavelength of light contributed to this. And the sharpest observation, the statistically most compelling observation, was actually made by an optical telescope in the Soviet Union. You know, who had ever thought of light contributing to something like this? What it is, it's a galaxy, that very common galaxy that has, it is active. It has a huge black hole at its center. It's like ours, but the galaxy is active. It's eating all its stars and whatever stuff, hydrogen there is in the galaxy, which ours is fortunately not. But that was the source, and the source that supplied the energy to produce this enormous luminosity of high energy particles. You see, these particles are rare, but they carry a lot of energy. And if you look at the total energy coming out of this system, they are enormous, but they are supplied by the gravitational energy of the black hole. So afterwards, we reconstructed what actually happened. And it took, so the alert was sent there, and you see this robotic telescope in Russia was looking at the source after 73 seconds. And it actually saw a huge change in the source 2 hours later. The source hadn't done anything for 15 years. They had been looking at it. And 2 hours later, it did the only thing it ever did in 15 years. So it changed its output by a factor 2. It was seen by Swift, Fermi, and then you have MAGIC, which is discovered it was a TeV source. And then there were all these optical telescopes, and they were trying to figure out the galaxy it came from. So we finally published that. And so there was this paper written by this huge collaboration of all these telescopes. But the interesting thing then that made it convincing for me at least, if you look at the accompanying paper written by IceCube alone, is so we now had a place to look in the sky, which is a lot easier than to look at 4 pi of the sky, right? So we had 9.5 years of data from that spot, which we had never looked at, which we had looked at, but not as some special direction. And so you just plot the 9.5 years of data, and you are now all looking at the wrong thing. This is what I've been talking about here. This is the neutrino with some other low-energy neutrinos coming with it. This is what we discovered happened in 2014. There was another huge burst, and in fact this burst from the source is responsible for the whole luminosity in the 9.5 years. It has 19 neutrinos on a background of less than 6, and it has a spectrum of e to the minus 2.2 for the experts, which is what you expect. And there are no gamma rays accompanying it, which was an interesting clue at the time. So now the first thing you ask, why didn't you see this before? It actually was in a thesis of a student at the University of Geneva. But if you don't have a special reason to look in that direction, you have all these trials you make when you look at all the other directions in the sky. That's called the look elsewhere effect. It kills this. So the optical telescopes, after a while, identified the source, the galaxy, and it's at 4 billion light years. Now, these active galaxies are not uncommon, and some of them are 10 times closer than this. So why do we see that one? So for every neutrino we see from that one, we should an active galaxy nearer, like the Markarian galaxies, we would have to see 100 events. Why not? So we don't see our galaxy, we don't see the nearby sources. I think it's a hint of a statistics of 1, that the sources are very special. They are not the average type of source astronomers look at. We analyzed our 10 years of data and found another active galaxy. It was marginal until we recalibrated and improved our detector and reanalyzed all our 10 years of data. And I cannot tell you what happens after that because it's embargoed by the journal Science. But we did discover something already that I can tell you about. NGC 1068, which is this galaxy, it's again one of these galaxies with a supermassive black hole at the center. And they have these very dense cores that flare in radio, and light doesn't get out, only X-rays get out. And so we have now evidence for a couple other of these sources, and so I think the picture is building up that at least it has something, the origin of the cosmic rays has something to do with galaxies. Obviously, this is just the beginning, and it's just the beginning, but it's a good beginning because as soon as we discovered cosmic neutrinos in 2013, the momentum of people doing this science built up enormously. And new players came into the game. So I'm probably leaving people out, but by now detectors are being built in water, which remember was Markov's original idea, in Lake Baikal in Russia, in the Mediterranean, in the South China Sea, and off the coast of Canada. Then there is another whole set of detectors that looks for higher energy neutrinos using radio techniques in ice or in air. And I wouldn't even trying to name all the projects. There must be like 30 of them. So this field is going to explode thanks to the information coming from all these new instrumentation. That's it. Thank you. All these young faces you see here, those are the ones who did it.
Thank you very much for your presentation. It was really interesting, and we have time for your questions. There is one.
I have a few mostly technical questions. First will be, what is the angular resolution of the detector in a typical event?
So the events that you saw here in these various slides, they have a typical angular resolution of 0.3 degrees, since we recalibrated the detector a bit better. That's not very good by astronomical standards, but it's good enough.
Yes.
Yeah, the goal is to make this better. We are working at that.
Then what is the expected lifetime of these photomultiplier tubes? And
Infinite.
Really?
We have lost, 5 to 10 but some of them have been in there since 2005. So if you do a statistical analysis, the answer is what I just said. It's infinite. But by statistical analysis, your lifetime is infinite too. You die from systematics. And so the thing is that eventually, the electronics, none of us can remember for how long the electronics is guaranteed. The electronics that captures the light and that digitizes it was built by a company in California. And we cannot remember whether they guaranteed 15 or 20 years. But in typical, these electronics last much longer.
Okay, so it's not limited by the photocathodes?
No. We don't. In the Amanda experiment, where we send analog signals, there we were destroying the photocathode of the photomultiplier. So there, that was a different story. But here, no problem.
Okay, and the last one, are they all pointed
down.
And does it matter with this size of
you know, remember this, this cone of light that you detect, it's 45 degrees, so even when it comes perfectly down, we still see it. So we have better sensitivity, but the difference is not big. Now, of course, we ourselves are planning to build a new detector 10 times bigger. In fact, we underestimated, we had never seen light propagate over a kilometer. Now we understand the optics of the light over a kilometer. So we're going to build next detector spacing the strings 250 meters. And so then you get 10 times the volume, 8 times actually, and fill it with the same number of photomultipliers. And but whether you point the sensors we are thinking of now have many small photomultipliers looking in all directions. It has two advantages. They are cheaper, and you can make the modules elongated, which means you can make put them in a smaller hole. It takes 2 C-130s of fuel to drill a hole, so you have to worry about such things. Thank you.
How come that the electron neutrino event was so strictly symmetric? How come that there is no directionality?
Because it's a shower, it's not a track. So the shower of that electron, when you simulate it, it has a size of 7 meters. And so a 7-meter shower in a kilometer cube detector is a point source of light, and that's what you see. And so they're difficult to reconstruct because, of course, they are not totally symmetric. If the electron comes this way, the light there arrives before the light there. But that's a lot harder to reconstruct than a track. And so that we can do now to 5 degrees or so.
Another question is, the way you reconstruct the energy and the direction, you reconstruct it directly from the data, or you use some templates, or did you have a library of many?
It's a straightforward reconstruction. Of course, now, in the last, everything now is done with machine learning. So I don't have to answer your question anymore. All the reconstructions are done by machine learning, by neural nets, the reconstructions don't become much more precise, but they take much less computing time. For a long time, we were limited in what we could do by lack of computing time.
So concerning these cases of electron neutrinos, you were mentioning that it was a big surprise for you to see actually them, yes? So why it was so unexpected?
No, it was a surprise because we were looking for events that had 1,000 times higher energy. And it was predicted that we should see 1 a year of those, and we had 2 years of data. So we were looking at events that, were like that, and then suddenly we saw what we were looking for, but it looked like that. But it was still big enough not to come from the atmosphere, or unlikely. So that was the surprise, yeah. We were looking for events that are made when cosmic rays hit microwave photons and then make a pion that decays into a neutrino. And those have 1 million TeV energy. These have only 1,000.
I would like to ask about the cosmic source of the neutrino. As you described that you hit this perfect signal. and then you look backward in the data and confirm it from previous data. Maybe I'm not understanding about the term of directionality, because I would expect, like, if I have telescope, let's say mirror telescope, I can aim it somewhere and I see. But I would expect IceCube would be omnidirectional.
That's the problem.
So, so it's a problem of like so much data that you need to look something a little above the noise.
It's a statistics problem. If you have no clue where to look, you look at the whole sky. And so our resolution, as I just explained, is less than a degree. So you typically look in a region of 1 by 1 degree, and then you look next to it and next to it and look at the whole sky. So when you found something like that, it could be a fluctuation, because you had looked like in 100,000 places. You are going to see something like this by accident. And so it had no strong statistical significance until we were told, look there, right? So it's called the look elsewhere effect. And you pay an enormous penalty when you try too many times. If you try enough, you'll see anything, right? That's how statistics works.
Okay, more questions? I saw that on the chat somebody commented that it might be a little bit better to have this presentation directly from the South Pole.
We have presentations from the South Pole. At this point, it's winter, right? So there are 2 people at the South Pole who are taking care of this experiment. And if everything goes well, they have nothing to do but give presentations. And so they cannot get in or out until November. So it's 6 months winter, and so they stay a whole year. And yeah, so they give presentations to high schools in the US, and so if you are interested and you want to organize that, contact me.
And maybe how it's difficult actually for young people to get into to South Pole, what they need to do
Well, when the experiment is running routinely like this, nobody goes to the South Pole except the 2 people I'm talking about. And by the way, if you are interested, every year you can apply. And it's amazing, you would say, who want to do this? This list, we have a list of overqualified people who want to do this. You know, these are, we have by now gone to 25 years or so of winter overs. We have, you know, they're fantastic people. We've never had someone who didn't deliver. So please apply if you want to do this. Otherwise, the only way you go to the South Pole is to install computers that have to be replaced every 5-6 years. But our NSF funding is not very good anymore, so that's, so we run our computers to death, so that's not a good ticket to go to the pole. But you have to wait until there is, you know, we are building this bigger detector, and then there will be lots of opportunity for everybody. And we will build it.
Dedicated for the experiment, or they are publicly available for the people to do, or to try to search for the
Yeah.
So do you plan to open it, or?
Obviously, the data we send as public alerts, they are public. And they are the most interesting part of our data. These are all our high energy events. But then we publish, whenever we publish data of any type, like the sky map I showed, it has, that data is made public as well. So you can find 9.5 years of IceCube data on the web to play with. And we have had many analyses done by physicists who don't belong to the collaboration. So everything we publish is instantly made public with the publication.
Maybe the students can ask some questions with something in your mind. Or you are already preparing for the subject.
Hello, thanks for your talk. I was considering that you found this very neutrinos that may be the source of cosmic rays. Unfortunately, these sources are too far away to be detected by the cosmic ray experiments. So I wonder if the sources are not so far away enough so that we can have some multi-wavelength observations and understand why they are so special compared with Centaurus A or another.
Well, Centaurus A would be a good candidate. We haven't seen it yet. So we have, we have 3 sigma evidence for more sources than NGC, and but not enough information to figure out what's special about them or so. But NGC is at 16 megaparsec. It's perfectly okay for Auger. And as you probably know, we have done analysis combining Auger and IceCube data and not found anything. You see, that's why I mentioned, we look for starbursts, for blazars, and I think the sources are special in the sense that to produce neutrinos, you need not, any electron can radiate a photon and be an accelerator in the sky. Here you need protons to be accelerated, and you need a target to produce pions to make neutrinos. So it's not surprising that this is not a category of sources that astronomers would recognize. And that's why this correlation business never worked. It also suggests that the sources are few, that there are not 10,000 vanilla AGNs that all produce neutrinos, active galaxies, sorry. Yeah.
I was just wondering, these new experiences you spoke about, there are going to be other types of detectors, like with IceCube or around array or something like that, complementary to the multipliers in the ice.
You're talking about the radio detectors?
For example, even water sharing contacts above ground and
No, all the detectors I mentioned that are being conceived or in construction, we are the only one that uses ice as Cherenkov medium. The others all use water. Yeah, and the radio detectors, of course, some of them use ice, and some of them just use the atmosphere as the medium of detecting, just like cosmic ray experiments. But they look for particles coming, which Auger does as well, right? Looking for particles coming through the Earth, up through the Earth. Well, that's difficult to say. You know, we obviously, if we have 8 times the volume, we will accumulate this at 8 times the rate. And so now you see maps with hundreds of events on it, 100 depending on where, you know, how you define them. Then you can imagine you'll see thousands where you now see hundreds of events. And more importantly, the angular resolution will be below 0.1 degree, or at least 0.1. So I think neutrino astronomy will be very similar to gamma ray astronomy, the way gamma ray astronomy is now, before CTA. And that's the hope. And then there, like in gamma ray astronomy, there will be multiple telescopes. So it will be a very different picture, yeah. That's my dream.
So my question is, don't you lose the angular resolution of the incoming events?
Yeah, that's a good question. So it's not just that, well, we should separate 2 things. We should separate the shower events, these electron and tau events, and the track events, where you see these long muon tracks. Clearly, the showers, you're going to detect 8 times more of them if you space the strings by 250 meters. Unless we make a lot of progress, what happens to their angular resolution is not clear, and probably it will not improve that much. The tracks, however, something I didn't explain is that most of the high energy events actually come along the horizon. These really high energy neutrinos, they actually, when they come from above, they don't make it through the Earth, which is kind of, you know, I told you they come from the edge of time and from the universe, but then when they arrive here and you're at the South Pole, they don't get through the Earth. But they always get through the Earth somewhere along the horizon, where there is not too much density along the line of sight to absorb them. So the most spectacular events come from along the horizon. And so when we deploy these 110 more strings that are longer, but still your detector is like a pillbox, right? So, so these tracks you will measure over 8 kilometers. And so the resolution will hopefully be much better. And our best estimate now is that we'll see five times more. These predictions are always wrong because you design your detectors with the knowledge you have now. When you actually build it, you have the knowledge of how the detector works, and then these detectors do much better than what you predict. But so at the moment, we will at least get a factor of 5 and a much better angular resolution.
You said that you found the ice at the South Pole to be a lot clearer than what glaciologists expected.
Yeah.
Do you now understand why?
Yeah, it's in fact you could well, I do and I don't. Let's not spend too much time on this, but what people had done is they had blocks of ice of a meter or so that they made from distilled water and bubble-free, and then measured the absorption length of light, and they got 8 meters. You could read that in textbooks. Fortunately, I hadn't read those books. And you know, what goes wrong with this probably is that you cannot match the purity of that ice. It's clear, and the better you purify the water. There's a place in Canada, it's a government lab, that actually purifies water to the point that they can make blue light, strength of light, travel 80 meters, but not more. Then you run out of purification techniques. So this is just, you know, snow from 60,000 years ago, and you cannot match that. Yeah, there are places where we find absorption lengths that are close to 300 meters, and it's incredible. Yeah, we had no idea what we would find. Also the bubbles, we thought the bubbles would disappear at 400 meters, and they didn't. They disappear at 1350 meters. The questions in the back there.
So, in how many years should the new detector be functioning?
Well, you want my time schedule or that of the National Science Foundation? There is no official answer to your question, but I can tell you what my idea is of what has to happen. We are doing something in, so you already got the idea that it's, you know, it's the 2 months a year, right? So in 25-26, we are going to deploy 7 strings which have nothing to do with what I talked about. It's to do neutrino oscillation measurements, but also to measure the ice better. And when we understand the ice better, we can again improve the detector with going to the 10 years of data. But so that means that we'll have the whole drilling crew, which is about 40 people, and all the technicians that build the modules, in fact, the modules for the 7 string are being built in Germany. And so it's really developing like a much more international project now. And so the idea is that in the 26-27 season, we start building the next detector, because you know, we are a university project, and so if we don't have research money to build detectors, we cannot pay these 40 people or more. So if it's going to be a successful project, so the construction will start in 26-27, maybe 1 year delay, but not more. And it took 5 years to build IceCube, so it probably will take 5 years again. There is talk about having 2 drills, so it may take less.
And how close would be the detectors to each other?
No, in the vertical direction, I've forgotten, they will be slightly closer. There will be longer strings with more modules. Do you remember the number? Between them, no, I don't need. But 250 meters from string to string.
No, I meant the distance from the 2 separate detectors.
Oh, no. It's built.
If it would be near each other or some 2 kilometers apart.
No, it's built around IceCube.
Oh.
IceCube will be in one corner of this detector. And the strings are deployed on a sunflower scheme, around IceCube.
The previous question almost touched what I wanted to ask about the new detector, and that's whether it will again be a cube or it will be more flat to accommodate for those interesting events coming from the horizon.
Yeah, it's, you know, it's inevitable, right? The ice is 3 kilometers thick. The first 1,300 meters has bubbles in the ice, which was a big surprise to the glaciologists, actually, because if you make a simple pressure argument, the bubbles should disappear at 400 meters, which most of them thought, but okay, we know the answer now. So you have to start below 1,300 meters, and then if you have a kilometer-long string, they will actually be longer, you are only like 300, 400 meters from the bedrock. So in this direction, you're totally constrained. And then if you space them by 250 meters, then you get kind of a flat, elongated detector, right? But then again, it does for tracks of high-energy events coming along the horizon, that's okay. Does that answer your question? Thank you.
So, who's next?
Maybe I have another question. You showed one picture to demonstrate the purity of the ice, where it seems that the sea is freeze. Is this a picture or is this a simulation? And is there a camera attached in one of those pictures?
Oh, you have, I could give, actually in 1 hour, I could not explain to you how we've measured the optics of the ice. But to give the short answer, yes, we have a camera in the, we had 2 actually, in the ice. We have, in every module in IceCube, there are 12 LEDs of 3 different colors, some pointing horizontally, some pointing away. And so what you do is you shoot this light from one module to the other. And you not only map where your modules are, you in the meantime figure out what the optics of the ice is. Because the photons scatter, of course, which we know, we only now begin to understand what the physics is. They seem to scatter at crystal boundaries. And there is dust in the ice, not much. The crystal boundaries we think is the main effect. But so we also have a YAG laser, which you can shoot different colors through the ice and measure the optics that way. So this was a long evolution. It took 10 years and is still going on. We knew it well enough to get IceCube funded, but we're still learning about the optics of the ice. We actually, the layering of the ice, we now know well enough that we can see individual volcanoes. There was a famous volcano 72,000 years ago that the geologists discovered in layers, and the glaciologists had never seen. And we actually resolve it with our measurements. So the volcano puts dust in the air, and the dust falls on Antarctica, and you can see it exactly where it's supposed to be. So that's already overkill. But there are other things of the ice, like one of the questions during the school, the ice in the refrozen hole. That's the next frontier that we have to understand in more detail.
Okay, more questions? If not, I think it's...
Once we get to volcanoes, it's time to stop.
Yeah. So let me thank you again. Thank you very much
It's a
for
pleasure.
being here with us.
Thank you. That's yours.
Yes.
Did everything go well?
Yeah, perfect. Maybe I will just clarify the answer. So, geologists expected that bubbles will disappear in 100 meters and
400.
400 and
Because of pressure of the ice
400.
on top.
And the reality was 300.
No, the reality was 1350. 1350.
Ah, okay, 130. Yes.
That's why the detector starts at 1500 meters.
Ah, yes, okay.
It's because, you know, when there are bubbles, there's nothing you can do.
Yeah, it's
It scatters the light.
Yeah, and there was this question about omnidirectional electron-neutrino event. So this because that if it's create a shower, the light of the shower goes backward. So so this is the reason.
But the light going forward goes first.
Yes.
And if you have nanosecond resolution,
you can see it there.
You can see the time difference.
Yeah.
And that tells you the direction.
Because I understand this question came from particle physicist colleagues, and they are used to just omnidirectional. They just see nice one direction.
Just see forward, tunnel vision.
Yeah, thank you.
But there was also he was saying that the odds for finding gravitational waves are 500. Loneliness was 66, but the gravitational waves was 500.
Dámy a pánové, tak to byl dnešní přenos a tím to končíme. A když tak, kdyby vás zajímaly nějaké další dotazy, tak napište do komentářů pod YouTube video a potažmo na naše Discordy. Na Twitchi to asi nenapíšete, ale napište to kdekoliv. Takže díky, že jste nás sledovali a nebojte se dopsat i zpětně nějaké otázky. A zase při nějakých streamech a videích s vzácnými hosty